Hello everyone, welcome to your chapter 14 video. This is going to be a tour of acids and bases over the next couple of upcoming videos. So in this video we're going to focus on checking out some common acids and their properties, some common bases and their properties, and we're going to talk about one specific definition of acids and bases. So as we move through this chapter, we'll learn two total different definitions of acids and bases. We'll talk about the strength of acids and bases, and we'll also talk about how we can measure how acidic or basic something is in the lab as well. So have you ever had like Warheads or Sour Patch Kids or Sour Punch Straws or Sour Skittles or Lemon Heads or you name it? Have you had a sour candy? Well, then you've experienced the power of acids hard at work in your mouth. You've tasted them, you know what they are. So acids tend to taste sour, so we often flavor certain kinds of candies with them. These candies are primarily flavored with citric acid. So citric acid is this acid that is found in citrus fruits, hence the name. So fruits like lemons and oranges, the sourness that you taste from them is from citric acid, and we actually are able to make citric acid so we can coat candies with it, and you can taste that sourness outside of just those citrus fruits. So different acids taste differently. Some of them are a bit more flavorful to us. You know, you can taste different hints of notes of other flavors, kind of cutting through some of the sour. However, citric acid to us tastes just generally pretty sour as an outright note. So oftentimes what happens when people make candies is if, let's say they're making a hard candy, for example, they'll start with the center of the candy and they'll coat it with some sort of more flavorful acid, for example, like the acid that's in grapes. So grapes have a little bit of acid in them. It's a bit more flavorful to us than the citrus fruit acid, citric acid is. So let's say we're going to put some of the acid that's in a grape on our candy first. Then it's often coated with some sort of time-release layer that takes your mouth a bit of time to break down. And then they're coated with citric acid on the outside of that. So when you put it in your mouth and you have your candy, you're going to get that strong sour pucker right away of the citric acid, but as your mouth starts to dissolve the candy, work through all the citric acid, work through that time-release layer, you get some of the more flavorful and less outright sour acids released. So I think the actual hard candy Warheads are a great example of how they've made candies and kind of used some of these chemical techniques to create an experience while you're eating your candies. So if you've ever had any sort of sour food, sour candies, you've eaten acids. And it seems weird because we think acids are dangerous, but we actually experience them in lots of different ways in our everyday life. So acids are compounds, of course, that have similar properties. If we're grouping things together, they're going to have similar characteristics, similar properties. Chemists love that. It's awesome. So acids are compounds that have sour taste, as I just said. So acids are going to taste sour. They can also dissolve many metals. We saw this in our very first experiment, the Evidence of Chemical Reactions lab, our first in-person lab, I should say. So when we were looking at this lab and completing the lab, remember we kind of took test tubes, we put some acids in some test tubes, and then we put some metals into our test tubes. And we observed that reaction for 15 minutes. At the end of it, in some of the cases, it didn't look like it changed that much. In some of the cases, it looked like, you know, that metal was gone. It was chunks. It was way different. And that's because acids are actually dissolving and breaking down those metals. So acids can dissolve many metals, not all of them, but many. You may have also seen this in like spy movies your book brings up, for example. So sometimes they'll try to get some acid to someone that's in jail so that they can, you know, use the acid to corrode the bars and break out of jail and be free and finish their spy mission, for example. So you may have seen that. That's real. It would take a lot more acid than they usually use in the videos. Nothing really is that corrosive. But it's a possibility if you had enough acid to sit there and work at it and work at it and work at it. You could eat all the way through a metal and break yourself out of jail. I don't encourage, but hey. So another place where you've experienced kind of some of this properties and some of the characteristics of acids is still in that same evidence of chemical reactions lab. We looked at litmus paper, so we didn't talk a whole lot about what it was. The background mentioned it just a tiny bit. But acid tends to turn blue litmus paper red. So when we were dropping all of the chemicals onto the 2 different colors of litmus paper, if you saw that blue litmus paper turn to red, that means that you had an acid. And that is something that we use to indicate whether something is an acid or a base as well. So there's lots of different color changes we'll see here with acids and bases as well. It's quite fun. So some common acids that you may have experienced or you may have heard of, I have them listed here. So first and foremost, acetic acid. So it's got the polyatomic ion acetate in it as an acid, basically. So you take that polyatomic ion, you add a hydrogen to it, and from there you're going to have acetic acid. We also know this in our everyday lives as vinegar. So acetic acid, we'll see it this week in lab. We're actually going to measure the concentration of acetic acid based upon some properties of acids and bases in reactions. So we'll see some of that this week. And, vinegar is an acid, and specifically acetic acid. So another acid that we've definitely used in lab that you may recognize is hydrochloric acid. So hydrochloric acid is actually your stomach acid. So you have a really, really, really strong hydrochloric acid in your stomach. And that's what breaks down your food for digestion into smaller pieces. It's what breaks down, for example, bad bacteria you may have taken in or something like that. So hydrochloric acid is in your body, floating around right now, yet it's still something we see in the lab. It's quite dangerous, but your body is able to handle it and control it and keep it in your stomach, which I think is quite cool. So if you have indigestion, for example, or you have some kind of like heartburn or acid reflux or something, we call it acid reflux because it's acid, this hydrochloric acid coming back up your throat, and that's why it kind of has a sour taste as well. If you've ever experienced that, is because acids have sour taste and you're experiencing that acid coming back up from your stomach, basically. So that's hydrochloric acid. Some 2 that we have seen in lab that you may recognize are nitric acid, HNO3, and sulfuric acid, H2SO4. We've seen those a little bit in lab. Sulfuric acid is actually the most highly produced chemical in the United States, fun fact. And so that's pretty cool. And one thing that chemists often use to remind ourselves as the dangers of lab is that H2SO4, sulfuric acid, is actually a quite dangerous acid if it's very strong. And so a little rhyme that sometimes we use to remember to watch our P's and Q's in lab is Johnny was with us, but Johnny's no more. What he thought was H2O was H2SO4 because they're both just clear liquids. If you're not paying attention to what you're doing in the lab, you might end up with H2SO4 instead of H2O, and that's why we also keep food and drink outside of the lab too, because things can be easily mistaken. So acids that are extremely concentrated and strong, like sulfuric acid, that are quite corrosive, can be dangerous to us if we're not watching our P's and Q's. So just a cute little reminder that we sometimes use in lab. And also too, some acids that we mentioned just a little bit before, but just to talk about them again, are citric acid and malic acid. Those are 2 just different acids that we tend to eat that make foods sour. So in contrast to acids, bases are kind of the opposite here. So we're going to position them kind of as opposite ends of a spectrum. So we'll talk about this, why it occurs chemically, why we consider them to be opposites of each other. But for right now, we can just kind of think of them as opposite ends of a spectrum. Acids on one side, bases on the other. If you're in the middle, you're neutral. So bases, some common characteristics of bases are that they are bitter tasting. So bases are often bitter tasting. So generally some bitter things you might eat or drink. For example, we'll talk a little bit about this, but coffee is bitter because of the caffeine molecules in it. So that caffeine tastes bitter. So sometimes it's an acquired taste. Bases also have a slippery feeling. So bases react with the oils on our skin to create this feeling. So just like when you wash your hands with soap, it feels slippery because it's kind of reacting with some of the oils on your hand as well. So anything that kind of has that real slick, slippery feel, like you could just slide out of your hands just like soap might, are going to generally be bases. And bases are going to turn red litmus paper blue. For example, in lab, one of our post-lab questions was to identify if NaHCO3, sodium bicarbonate, is acidic or basic, and this was what was meant to be your hint in lab, was that when you tested NaHCO3, you were able to see that it turned red litmus paper blue, and that would tell you that you have a base, for example. So let's go through a list of common bases that you may, hopefully some of these not have experienced, but you may have some knowledge of or have used in some way in your life. So the first one here is conine. So this is the poison that's in hemlock. So bases are bitter, and bitterness is often an acquired taste. Lots of people don't like bitter things, and we think that it may have something to do with this, right? So conine is a very bitter taste. It's the poison in hemlock that could kill us. Lots of the poisons in plants are bases with extremely bitter tastes. So lots of times people have this taste aversion to bitterness, which could be due to the fact that lots of poisons are bitter, and our bodies, our ancient ancestors were like, no, don't eat the bitter things. For example, coffee and tea tend to be a acquired taste because they're so bitter, or like really, really hoppy beers, for example. Those are often acquired tastes too because they can be quite bitter. But for example, there are bases that we can eat and drink, like my favorite base and one of my favorite chemical molecules, caffeine. So I can't get through the day without my bitter tasting caffeine all the time. So I'll take it. So caffeine is another base that you may have experienced in your everyday life. Soap, as we talked about before, soaps tend to be bases. They have that slippery feeling. Drano is actually one of the main components is sodium hydroxide. We've seen sodium hydroxide in the lab as well. We've used it just a little bit, but sodium hydroxide is a relatively strong base, so it will sweep everything out in your pipes and kind of get through there. Bases are often used as cleaners and cleaning products and things like that. Another one you may have seen, I brought it up just a little bit earlier, is sodium bicarbonate, which is NaHCO3. Bicarbonate is this polyatomic ion you see here, HCO3. This is baking soda. So if you've used baking soda, you may have done that while you're baking so that you could create bubbles and make your bread nice and light and fluffy. But we also use sodium bicarbonate as an acid as well. So like if you're having that acid reflux, you're getting that sour taste up in your mouth because you have just a little bit too much acid in your stomach or something like that, you can take a base to do some kind of neutralization. We'll talk about that in a little bit in lab. But we'll talk a little bit about neutralization. So you're going to neutralize some of that acid so that you can try to get rid of some of that indigestion, heartburn kind of a deal. So we kind of have these acid-base reactions happening in our body quite often, and we can kind of use some of these acid-base concepts. For example, here, I've got so much acid, it's coming up my throat. I'll have just a little bit of a base. That way I can kind of neutralize some of the acid, get rid of some of the acid in my stomach, and it won't be quite so uncomfortable for me, for example. Another base that's very common that you may have heard of that we're going to talk quite a lot about this chapter is ammonia. So ammonia is a cleaner. Often we'll use it in our homes as a cleaner. It's also a fertilizer, or used to make fertilizer or in fertilizer, for example. You may have experienced it that way. It's also used in explosives manufacturing as like a place to take a nitrogen from, because lots of explosives are based upon nitrogen bonds. So ammonia is kind of a heavy lifter. It does a lot. And if you check out your book, it has a list of common bases with lots of the different things they do. So this is just touching on these common acids and bases. But you should totally check it out and kind of see if you can't research some of the acids and bases you experience in your everyday life. Okay, so now that we've talked a little bit about common acids and bases, we kind of have a little bit of a setup there. We also want to talk a little bit more specifically about some chemical definitions of acids and bases. So we kind of talked about how we experience them in our everyday lives, but how do we talk about them in chemistry? In this class, we're going to learn 2 specific definitions of acids and bases. We'll talk about why we have 2 different definitions, and to be honest, secretly, we have more than 2. Once you get into higher level chemistry classes, you'll learn, for example, Lewis acids and bases, and a few other bigger definitions, broader definitions of acids and bases too. So these are the 2 we're going to talk about in this class, but hey, lots of definitions of acids and bases. So Arrhenius acids and bases are what we're going to talk about first in this video. So the Arrhenius definition of acids and bases focuses on the formation of ions in solution. So these look just a little bit more about what the original compound is, not necessarily how it behaves in a reaction. So Arrhenius acids form an H+ ion in solution. And that's how we can identify an Arrhenius acid. If we can put something into solution and it dissociates so that it has an H+ ion. So you may remember when we were talking about naming compounds, we talked about ionic compounds, we talked about molecular compounds, but we also brought up naming acids as well. And so when I positioned you for this, we talked a little bit about how acids are kind of a mix of an ionic compound and a molecular compound. So we're going to talk about that a little bit again here. So while they are technically molecular compounds, they tend to form ions and ionize in water. So if something ionizes, it forms ions. We might also call this dissociation as well. So they're going to break into H+ and the other ion 9 times out of 10. We'll talk about polyatomic ions being what's broken off. But that's kind of the idea here. If we can find a way that it dissociates into that H+ ion and something else, a negative ion, it's likely going to be an acid. Ooh. So that being said, one way you can identify acids along the lines here is that it might have a hydrogen out front in the chemical formula. So this is the hydrogen that is able to be ionized and become H+ in solution. So for example here we have formic acid, and formic acid has the chemical formula HCHO2. Now we have 2 hydrogens here, however only one of them can be ionized into that H+ that we could find in solution that we could use for our definition of an acid. So it would be this front H molecule or H ion that could be pulled off, and then you would have hydrogen and then formate, the formate ion here. So that's kind of how it works. So if you're looking at a chemical formula, it kind of maybe has one of these standalone H's out front. That can be an indicator that you have an acid that is able to dissociate in water. So I have a couple more examples here. This is our friend acetic acid, the acid in vinegar again, that we're using in our titration lab. And it dissociates into H+ and C2H3O2, which is our acetate ion. So we can kind of see that we have some sort of ion that we might be able to dissociate with. And here is nitric acid, which is HNO3, which breaks into that H+ and NO3. So it's important to kind of remember it's the hydrogens that are out front that will be ionized. So if I ask you, how would this acid ionize in water, you should be able to understand that it would only be the hydrogen out front, for example, that would be ionized in this case. Okay, so when we're talking about Arrhenius acids, I brought up this H+ ion. I want to take a quick moment to talk about the H+ ion before we move on to the Arrhenius base definition. So this is going to be kind of important as we start to differentiate our are definitions of acids and bases, Arrhenius versus, spoiler alert, Bronsted-Lowry. So I want to have a little bit of a conversation about the H plus ion. So let's think just a little bit about what an H plus ion looks like. So a normal hydrogen atom is made up of 1 proton, 1 neutron, 1 electron. So that would be the charge neutral atom. So we know it has 1 proton, it's number 1 on the periodic table, it's going to have 1 electron to balance that out. So if we have an H plus ion, so we have something that's 1 positive, well, I must have removed my 1 electron from my atom to make that happen, right? So that I have 1 proton, no electrons, that's a positive 1 charge. So if we have an H plus ion, that means we removed the electron from our hydrogen. So we're literally left with a proton and a neutron in this case. We just don't care so much about the neutron. So oftentimes we call the H plus ion literally just a proton. So if I'm talking about a proton, I mean the H plus ion. All we're doing is calling it as we see it. That's what it is a proton. So if I'm talking about the H plus ion, I may call it a proton. If I'm talking about a proton, really likely here when we're talking about acids and bases, I'm talking about that H plus ion. When H plus ions or protons are in water, they react with the water to form H3O plus. So that H plus ion, obviously it has no electrons. It's just this 1 big positive charge floating around. So it's going to buddy up to the water molecule so it can share some of those electrons, some of that negative charge. So if an H plus ion is in water, oftentimes it forms H3O plus. So we can often use H plus, H3O plus, and proton interchangeably based upon the need of the situation. We'll see later in this chapter where we might use some terms like H3O plus and proton, but for right now, as we're talking about Arrhenius acids, we're only just kind of thinking of it, for example, as giving us that H plus ion, or again, I may use the word proton there, for example. So, just a quick note about H plus, about the way it behaves, and why it's kind of cool. I don't know. I think it's kind of cool that it's a proton with no electrons, man. I don't know. It's kind of a bizarre thought to me that you can have an atom with literally no electrons, and I don't know why that's so bizarre to me, but it feels cool thinking about it as just a little proton floating around. So that's just a quick note about H plus. Let's talk about our Arrhenius acids and bases. Arrhenius bases. We already talked about the acids. But so the Arrhenius definition of acids and bases, if we're going to focus on the base aspect of this, is that Arrhenius bases form the hydroxide OH minus ion in solution. So this is one of those polyatomic ions you really should be able to recognize. It's going to become your best friend right about now. You're going to know it. We saw it a little bit in the observation of ionic compounds lab, Arrhenius bases form the OH minus hydroxide ion in solution. So if you have NaOH, that splits into Na plus and OH minus in solution. If you have KOH, that splits into potassium 1 plus and OH 1 minus in solution. So that's kind of basically all you're looking for with your bases is the OH minus in the chemical formula for an Arrhenius base. As you may have picked up by that, this definition is extremely limited. So the Arrhenius definition of acids and bases, it was basically a jumping off point for scientists. So this definition was one of the first kind of conceptualizations of acids and bases as how they behaved on a molecular level. So how those molecules are actually behaving to be acids and bases. However, it's limited for a couple of reasons here. So even though it was our first idea, I don't think it was likely our best idea, and we tend to default to other definitions beyond this one. So it assumes that everything occurs in solution, which is not always the case. Acid-base reactions, for example, can occur in the gaseous phase as well. So you may have two gases that are interacting with each other having specifically an acid-base reaction. So that doesn't really work well if it's based upon the definition of is the molecule able to form H pluses or OH minuses in solution, well, it doesn't really help if it's occurring in the gaseous phase. Well, the other thing that's kind of funky here is that it assumes all bases contain OH minus in their chemical formula. So we know that's not true. We talked about ammonia before. Ammonia is NH3. There's no OH ion in there. There's no hydroxide ion in there. So we know that's not true. So even though this was like a good jumping off point, it was a good working definition for the time. Arrhenius acids and bases was kind of like, again, the first stab at it, but we'll get to learn just a little bit more about a more complex definition that's broader and helps us apply the term base to compounds like ammonia that don't necessarily have that OH minus directly in the chemical formula. So that's a little bit about Arrhenius acids and bases. So I hope that you would be able to look at a chemical formula, start to be able to determine if it's an acid or a base, and be able to apply specifically this Arrhenius definition of acids and bases. If you can look at the chemical formula, determine if it could deliver an H plus ion when it's in solution, or if it can deliver the OH minus ion in solution and would be considered a base. So that's kind of what I'm looking for out of this chapter. Or this part of the chapter, and we'll get to talking about our other definitions of acids and bases, as well as what it can mean to measure a compound in the lab as acidic or basic.